All right, so let me introduce our next best paper candidate, Akram bin Ahmed, and he's a senior research scientist with the National Institute of Advanced Industrial Science and Technology in Tokyo, Japan, and he's going to talk about Ethernet frame crafter and capture for TSN research. Okay, let's welcome Akram.
Okay, thank you very much. Can you hear me? Okay, thank you very much. Good morning, everyone. Thank you for joining our session. It's a pleasure to present to you our latest work where we propose a measurement tool that is efficient, accurate, deterministic for TSN or time-sensitive network research and development. So this work is part of the big national Japanese project where the main purpose is to propose or to integrate the next generation of post-5G communication information infrastructure and systems. So I was just like coming to the station and realized that I'm gonna preach a lot about time sensitivity and deterministic. So I will do my best to make my presentation deterministic and respect the time sensitive schedule of this presentation. So this is the roadmap, and let's dive in right away to what is TSN, what are the opportunities, the key feature, and the challenges. So as you may know, there are a lot of emerging applications in the past years like 5G, smart manufacturing, smart cities, and so on. And these applications actually they are very sensitive to latency. And these latency sensitivities actually requires that it should be in the variation of like scale of microsecond or even nanosecond scale. So time-sensitive network or TSN come as an answer to respond to these demands by proposing some kind of like a new standards or like adding standards to conventional Ethernet to provide determinism, ultra reliability, and ultra low latency. And it offers a lot of features like deterministic latency that can be used in smart manufacturing, also traffic scheduling where like reserved fixed slots for high importance or critical data, and also allows, like I said, both Ethernet, conventional Ethernet, and TSN to coexist in the same network, which offer interoperability. So how does a TSN switch work? Like, this is a very high-level overview of a TSN switch. So the basic idea, if I can put it in a very simplistic way, is that TSN basically control the frame interval. So if you have a flow, you control the traffic by changing or controlling the frame interval between this traffic. So, and this is done according to predefined algorithm, what they call the shaping algorithm. So basically, the TSN is based on two major importance factors. The first one is the traffic class, where each input port or each port has up to 8 traffic class queues. And for each traffic class, you have a priority. The higher the priority, the better, like the more allocation of resources, and you give it over low priority ones. So, okay, sorry, I'm not sure why the overlapping. So the main idea is if we have like a traffic, like a flow here, for example, what it does is that when it enters an input port, first, like the destination of this flow is determined in the filtering database. And then using the traffic shaping model, which can be a credit-based shaper or asynchronous traffic shaper, will control what we said earlier about the frame interval to control the burst, to control like the congestion ahead of the network. And finally, talking about the priority, the arbiter will control the priority. It gives higher priority precedence to like be forwarded within the network. So following this, when we started this project, one of the first things that we noticed is that most of the TSN work that has been done so far focus on only simulation and theoretical, let's say, analysis. And another frustrating one was that like commercial ones were very closed. They are not easy to fix, they are not easy to modify, and they are quite expensive. So one of the motivation or what we end up doing is propose this ITSM project, where the main idea is to propose a hardware design support that is open source in order for TSN researcher to develop, to analyze, and to have more accurate and fine-tuning evaluation of their research. So we propose so far 2 flavors of like a L2 network switch, one supporting credit-based shaper, and one supporting asynchronous traffic shaper, ATS. And we're going to focus on ATS because it has shown its superiority just for this slide to understand what is important about like TSN. So ATS is eligibility time system where like a frame is forwarded when its calculated time is reached. The primary goal, again, as in TSN, is to reduce jitter, to guarantees determinism, and also to ensure that the worst case end-to-end latency meets a predefined requirement. Another important feature of ATS is that it supports multiple flow within a traffic class. So a traffic class, we said earlier that we have up to 8 traffic class. The good feature about ATS is that you can have many flows that belong to the same traffic class and coexist together in the same network. So when we focus on this multiple flow, as we can see here, we have like multiple flows that enters randomly the ATS schedule, and when they get out, you can see like each one of them has different frame interval that is predefined by the user and achieved through the ATS schedule. So we have been boasting a lot about how TSN is great and everything is good and it like opens a lot of horizons for research, but actually it's quite challenging and it's not that easy, especially when it comes to measurement, which is the focus of this work. So as any like a measurement tool, whether in conventional Ethernet or any network study, probably the first, let's say, goal is to prove concept, to see the limits of a proof of concept. But when it comes to TSN, it adds another layer of complexity because you need to minimize the variation within a few seconds and like troubleshoot complex and transient timing failures. So the problem with the existing solution, the first one is, as I said earlier, most of them are based on software. So there is a huge problem of jitter in the microsecond level. Also, we have missing capability, the inability to mix multiple flow that I explained earlier in the previous slide. And like I said at the beginning also that there is a problem with hardware tool, complexity of hardware tool. They're not very open and it's very difficult to adapt these hardware tools to some specific custom modification or analysis that a user might have. So focusing on this software tool, so we conducted an experiment where we had 2 host PCs that are equipped with a commercial Intel i210 network interface. These network interface will exchange data. One of the good features about this Intel i210 is that that has a hardware offload option. So it's kind of like a partial hardware support. So this hardware support, if it's enabled, it allows us to use a hardware clock. If it's disabled, then we will rely as in a normal network interface on the OS. And when we see the evaluation, we see that without the hardware clock, without the partial hardware support, we are in the 130 microsecond range. And when we enable it, we have 80 nanosecond range. It's good, it's very improved, and we can see the difference that the hardware can offer, but at the same time, it's not enough. Because when we check the target requirements for several, let's say, TSN application, like 5G, for example, it's actually within the 10 nanosecond. Other, like, for example, power grid, under the 80 nanosecond, like 50 and 100, between 50 and 80 nanosecond for example, automotive ADAS systems. So to summarize, so far I've been talking only about like the motivation, it's very important, but to summarize, we have witnessed like a shift in focus. Like TSN is no longer this theoretical or let's say paperwork research, but rather is moving step by step steadily towards like practical implementation. And that's the goal of the main project, the whole project. Also, there is a practical requirement. Not only we need few nanosecond variation, but also we need the ability to mix multiple flows within a traffic class. And finally, there is a crucial need for this requirement to be satisfied by offering a customizable, accurate, and deterministic solution by generating traffic accurately, capturing traffic accurately, and being able to easily configure, because TSN is also evolving with time, so you need to be able to adapt to this evolvement. So what we're proposing is a solution that is based on FPGA. I'm not sure, probably a lot of you I've met, like, throughout my career, a lot of people who hate hardware or then don't want to know about it, but field programmable field programmable gate array is one of the good technology, or the nice technology that offers flexibility. So which is based on this proposal solution. We call it like EFCC, Ethernet Frame Crafter and Capture. So it's precise, it gives a flexible, concurrent system supporting like multiple flow in the nanosecond range of accuracy or like variation. Plus, it's an open source, and it can be, and it's available on GitHub, so you can use it, modify it, and build upon it. So I'm gonna give a little bit of hardware, if you don't mind. So here, FPGA, this is the architecture of EFCC. So what we have here is working as a 1 Gbps the maximum speed. It supports between 64 and 1522 bytes, depending on whether a VLAN tag is added or not. And it's prototype on a KC705, AMD Xilinx KC705, since it has only one FPGA port, Ethernet port. So we opted also for this Ethernet eFMC, which allows us to 4-port. So this is a photo of the exact of the system. So this is the FPGA board, and you have here mounted a daughter board Ethernet FMC. So not going too much into details, and we're going to focus on two major components, the key components of this architecture. The first one is the frame generator. So what the frame generator has, it has, sorry. Okay, I'm going to follow this one. So what the frame generator has, it's composed of the core model. Here, the green one. The green one here. This is the core model, is the core model or the main core component responsible for generating the traffic or the frames. And what does it do? It will refer like to several buffers here. The first one is the frame transmission info. So it has all the entries required to generate a given traffic. And it has a frame entry here, a NOP entry, and end of length entry. So the frame entry is the frame that you want to send. Then you have the NOP entry, which control the interval between the frames that we mentioned about. So how does it work? Okay, so first, users from the outside using a simple host PC, they can configure the transmission information buffer, the sequence of frames that needs to be sent, and also like they define the MAC address and the IP address. Second, the core model responsible for generating frames will read this information and generate the proper frame sequence that it will be sent through the AXI4 stream or like the downstream node. For the second major component for this presentation or for this work is this timestamp recorder. To be honest, it's to avoid like this is a simplified like version of the module for ease of understanding. But the basic idea, you have a write stamp module which will fetch the timestamp from a given frame, and it will store it in a timestamp buffer. And we have two of them. One for the TX means outgoing frames that goes from the EFCC, and then you have a write or like receiving write stamp, which is for the receiving part of the composite. So let's move to the evaluation and the environment of result. So what we tried to do is at first, since we're building this from scratch, is first of all, we need to have a measurement validation. So what we tried at first, again, we tried to use commercial product. Unfortunately, they were unstable. We think it might be possible due to the issue between the sender and the receiver appliances. So what we did, we opted for a simpler yet effective method, which is to use or to measure the latency or the timing through different cable, a Cat6A Ethernet cable with different sizes, from 2 meters to 100 meters. For over 30 meters, we used RG45 couplers, and we made sure that their latency is not, let's say, considerable. And we compare the measured value with the theoretical value that we achieved or like we got from the data sheet. So what we did is, like I said, we mentioned this. We have here, sorry. So we have this, we can see that the exact, basically the exact matching between theoretical and measured value. We sent almost 1,000 frames with 2 different frame sizes, and we see that like in the speed 66.7 of the speed of light, which is somehow the standard specified by the data sheets of the cable. And this is to conclude that the measured latency actually matches the theoretical one. So that gives us a basis that we continue further with our evaluation. So first of all, we made the frame capture capability. So for neutrality, we wanted to use a third-party component, which is what we used before, is I210. And we connected it sent like some frames through a 1 Gbps, exactly back to back. This is very important because when the frame size is fixed at a lane rate of 1 Gbps, then the frame interval is always constant. So we can control the frame interval through defining or varying the frame size. And we repeated the experiment with different frame sizes, and we captured the recorded frames with our timestamp recorder. So the result shows that we almost had 98% of the capture frame interval were exact match, a 672 nanosecond reference frame interval. And when we increased it, still remained in the 97% of exact match. And we have a variation for both of them in the plus minus 8 nanosecond. So we think that the possible jitter is due to the PHY IP, the physical PHY IP of the FPGA, that we do not have any control over it. Still, we think the 8 nanosecond is very inevitable, unfortunately, but still good and acceptable for our application. The second is the frame generation capability. After seeing the capture, frame generation capability. So what we did is we connected the same thing for the sake of neutrality, the frame generator, to a host PC that has a network interface, and it has like TCP dump. We capture the frame through TCP dump. And we define the sequence in the frame generator here that has predefined yet randomly chosen values like the VLAN tag, PCP code for priority, MAC address, frame size, and also frame interval. And what we saw is that we observed that, first of all, the most important thing, no frame loss. And the captured data matched the sent sequence. Second, the difference between the specified that we specified in the frame generator and the one that was captured by TCP dump was around like an interval of 3 nanoseconds in total. So, but the key, let's say, feature here, or the key result here, is that we have a variation between 8 nanoseconds and 16 nanoseconds. So, to see what is the culprit here for this variation, now we made the full EFCC, means an EFCC frame generator and an EFCC frame capture. And what we saw is that actually the variation was almost 8 nanoseconds all the time, and in a symmetric way. So that's why we can see like this flashy 0 nanosecond. But the most important part about this result is that 8 nanosecond, and no matter how many times we repeat this experiment, it did not change. So the next evaluation is the latency bound of the multiple flow. This is multiple flow is very important for TSN and for ATS. And as I mentioned earlier, we previously provided or proposed an ATS-based switch, open source, FPGA-based, and so on. But at that time, we could not measure or like evaluate this feature of multiple flow because simply there is not a single tool, measurement tool that can provide this. So this is the perfect candidate for our evaluation. So what we did is that we have connected our EFCC with our previously proposed TSN switch, and we sent like 3 traffic. One is ATS, TC7, highest priority. There is a TC6, mid priority, and then is TC5 with strict priority. And then what we achieved is we compared the measured value with the theoretical latency bound calculated through from like previous work. So when we talk about the highest priority, TC7, we saw that 24.6 and 23.2 microsecond was the approximately contention delay. That is way below the latency bound calculated at 37. The same thing with TC6, which is the mid priority. We have 47.7%, which is again low than the below the theoretical upper bound. Finally, for the evaluation, just to give an idea, we are within a reasonable amount of lookup tables, flip-flop, and a lot of hardware resources. But when it comes to block RAMs or the memory, we are reaching the limit. But it's very important to mention that the used board is very affordable. Means like it's made for low power and does not have a lot of resources. It's good for proof of concept, but in case user wants to use a lot of resources or have a higher, let's say, utilization, they can easily modulate or like port this design to other FPGA board. So finally, so what we're trying to propose here, or what we propose, is kind of like a frame generator and capture system that directly address the critical research gap. There is a huge critical gap between the variation, the multiple flows within a traffic class. But even though it's for TSM, but it's very important, and we encourage a lot of like an audience here to use this EFCC even for various network study, because it's highly modular, it's highly flexible. You can remove actually the entire TSN feature of it to use your own. Second of all, like I said, we succeeded to handle like a multiple flow in the nanosecond accuracy, and it's open source, portable. So again, we encourage you to use it. So as a future work, we want to use more complex situation, because the end goal of the entire project, like this national project, is to deploy this technology with multi-edge access computing. So we need to apply it for further complex situation. Also, we want to like scale up to high speed, even though like probably 2-3 weeks ago, we actually succeeded to make the whole framework for 10G, including the switch and the measurement tool, and hopefully it will be published soon. Finally, we address the optimization of configuration of TSM, because it's not only the hardware architecture, but another challenge is actually the configuration, how you select the traffic classes and how you deploy them in the whole network. Finally, repository in GitHub, it's under permissive license MIT, and we provide Jupyter notebooks. So don't worry if you don't know anything about hardware, or you don't want to, let's say, bother yourself or like waste your time learning Verilog and all that stuff. Leave it to me. What you have to do is just go, know basic about Python, run. There are several examples. There are a lot of artifacts that you can use. And I hope you can go ahead and have a look at our repository. Thank you very much for your time. And please let me know if you have any questions.
Thanks, Ahmed, for a very interesting talk. And it's time for questions.
Hi, thank you for your great talk, and I think such open source hardware should be a great contribution to the community. And one simple question is that if I understand correctly, there are a couple of not so many, but few commercial conformance, performance testing tools. So have you ever compared with those?
Okay, that's a very good question. So for the commercial part, we have two things. First of all, the switch. For the switch, yes, there are a lot of I wouldn't say a lot, especially when it comes to ATS, the one that we're focused on. I think there are couples, okay? And we tried one. And unfortunately, we could not, let's say, it's not that flexible. So this is, it started like the whole thing, like the whole quarrel started out of frustration, let's say. He said, you know what, I'm going to start make my own. But when it comes to measurement, actually there is none. There is not a single, even to the best of my knowledge, either academic or like commercial one that provide ATS support for TSN and mixing multiple flows. So that's why, again, like in the previous work, we wanted to evaluate that. And as you know, we have the fund to buy like those commercial like product, but we could not. So that's why we needed to build our own.
I see. Thank you.
So thanks for the talk. So you're using a hardware-supported approach, using FPGAs. I would say in the networking community, many people have been working on SDN-based TSN supporting solutions using, not hardware support, but at least configurable switches, P4, and this stuff. Have you compared your work against this still software, but low-layer software-based SDN-based approaches which have been around for a few years now?
If I understood correctly, I think you're talking about, for example, the Tofino switch. Yeah. So the Tofino, unfortunately, we did not compare because, to be honest, I felt like it's not fair for comparison because the Tofino is actually, you have the hardware and you configure it through software. Yeah. But for us, we wanted, like, the whole purpose of this project is to have a standalone, like, completely. You don't need any commercial one. You just download this. At the end of the day, FPGA, you can consider it as a bit stream, means like a software in a sense. You're going to have generate a file, and then you can download your file to the whole thing. But it offers you a lot of, let's say, flexibility. Because the Tofino, at the end of the day, you cannot change the architecture inside. You're just going to use that architecture and configure it to the best that you can. What we're offering is different. We're offering you, like, unlimited possibilities. You can buy any FPGA one. I'm using like the KC705, but you can use a smaller one or a bigger one or even high-end one like with hundreds of thousands of dollars if your budget allows it, and you can build your own. So that's why I felt probably it's not a fair comparison because the target is different. So I'm not sure if I answered your question.
Yeah, got it.
Okay, thank you.
If not, given the time, let's thank the speaker again. So he will be around.
Thank you very much.
Talk to him at any time.